Hello everyone, my name is Nitin. I'm going to make a presentation for this course of Instrumentation and Control of Energy Systems. My topic of presentation today is techno-economic optimization of a zero-emission energy system with battery control for remote community of Makowik, Labrador. My project is supervised by Dr. Mohsin Jamal. We know that in today's world, conventional energy sources are being replaced by cost-effective sustainable, renewable energy sources, which are environmentally friendly and are available in plenty. The availability of renewable resources are intermittent in nature and have a major factor in choosing a resource for energy needs. Research and development has been done in designing and optimizing and obtaining full control of hybrid renewable energy systems, which ensures constant energy without any intermittency. For this project, we are going to do a techno-economic analysis on a hybrid wind solar energy system with zero emissions for a remote community of Makowik in Labrador, Canada. Here, we are going to employ softwares like Homer Pro and MATLAB Simulink to forward this process. The community of Makowik is located in the remote part of Labrador, and access to this community is very difficult. We need to create an off-grid energy system to serve the load requirements of this off-grid isolated community where there is zero chance for any energy source to come through. We Here we create a proposed model and do its techno-economic analysis along with its storage requirement and work on solutions for improving the storage capacity and longevity of energy by using state of charge control and constant current and constant voltage control. The remote community of Makowik is located in Labrador, which is in the province of Newfoundland and Labrador. It is a very remote, isolated Inuit community with a population of about 360 people. It is located 55 degrees and 7 minutes north and 59 degrees and 3 minutes west, which would be approximately around 210 kilometers northeast of Happy Valley Goose Bay by air. The landscape of Makowik is characterized with rough terrain, rocks, outcrops, and very rocky and hilly areas. As the remote community of Makowik is very isolated, it is very difficult to access the community and thereby very difficult to introduce a proper grid system to supply constant power to the community. So alternative methods have been developed so that the community of Makowik, which is an isolated community, can satisfy their needs of energy. It would not be wrong to state that introducing a grid to such a small area, which is so distant and isolated for such a small population, would be economically not feasible. On looking at the load requirements of the community of Makowik, which is a population of around 360 people, assuming an average of 4 people in a household, the number of households in the community of Makowik rounds up to 90. The average electricity per household, as per ENA data, is in 2021 is around 11,135 kilowatt hour. So from that value, we can calculate the annual energy requirement for the whole community of Makowik, which can be depicted in table 1. We can also determine the net peak load in kilowatts and the monthly energy consumption in megawatt hours from figure 2 and 3 as shown in this slide. Here in the figure 4, we can see the proposed model of the hybrid solar wind powered hybrid energy system with the charge controller, battery charger along with the inverter unit which runs and satisfies the AC load for the community. Here, the output of the individual renewable energy sources are combined together and fed into the charge controller, which first and foremost charges a battery bank to act as a residual storage to counter the intermittent nature of renewable energy sources. The rest of the energy is given to the inverter and converted into an AC supply and fed into the AC load to satisfy the energy requirements of the community of Makawik. On conducting the techno-economic analysis for the proposed hybrid system, whether the following parameters are shown in Figure 5, a complete view of all different components of the hybrid system are depicted. Here, in Figure 5, we can see that the total load of the system is around 2,831 kilowatt hour per year, which is used to satisfy the load. We are using two renewable energy sources, that is a solar energy source rated at 500 kilowatt and three individual 250 kilowatt wind turbines. To have residual storage capacity of around for the storage that is required, 500 3000 ampere hour batteries are used, and the energy from each individual sources are converted using a 1000 kilowatt multifunction converter unit. On analysis of the techno-economic data obtained on conducting the techno-economic analysis of the hybrid energy system, we get that the total cost, that is the total net present cost of the entire hybrid system is around 341,000, and the level cost of energy for the entire hybrid system is around $0.09 per kilowatt hour. The operating cost of the entire system is around $14,359 per year. The storage element in the wind hybrid solar energy system plays a very important role as it ensures constant availability of energy. So it is very important to make sure that the storage elements remain intact and works 24/7. So we have to protect the batteries from various faults that may occur due to continuous working of it or charging and discharging in a pretty rapid manner, which will cause or in an erratic fashion, which will cause for the batteries to heat up and eventually head to thermal breakdown of batteries. This phenomenon is also known as thermal runaway. Here in Table 3, we can see that the total amount of energy that goes in and out of the batteries, along with the storage depletion losses and annual output of the battery, and its expected life, along with its nominal capacity, autonomy, and battery wear, and its cost related to battery wear can also be observed. One of the very common methods to control thermal runaway and improve the lifespan of batteries would be to control the state of charge or SOC of the battery. The state of charge of the battery can be simulated in MATLAB software. We can see in Figure 6 that the proposed model that keeps the battery SOC between the desired limits that we so choose. Suppose we want to keep the charge, that is the state of charge of the battery between 40 and 80%. So by this simulation, we are able to make sure that the battery always remains between 40 and 80%. The state of charge block or the state flow block is used to get the batteries in between the values that we so desire. The percentages of the SOC that needs to be maintained so that no fault can occur in the battery is the best way to move forward so that the state of charge control can be implemented inside the battery. So we can easily define the peak charge and discharge that is needed for the battery so that a thermal runaway never occurs inside the battery. The state flow block is used to control the charging and discharging process inside the battery. In Figure 7, we can see how a state flow block operates. Here we can see that two blocks with directions or processes that are defined on the blocks. Here the process is set in such a way that if the charge is below 40%, the charge block gets activated. That is, sorry, that is the pulse signal turns 1 and applies to discharge block simultaneously. becomes deactivated or the pulse signal becomes zero. And vice versa when in the case of the discharge block. That is when the battery charge goes beyond 80%, the discharge block, the pulse value becomes 1, and for the charge block, the pulse value becomes 0, thereby initiating the discharge process inside the battery. The time period for this discharge process may also be set by using rational operators, which can be seen in the model diagram in the above slide. Here in figure 8, we can see that the state of charge for a time period of 100 seconds. Here we can see that when the state of charge of the batteries is around 80% and at 50% the discharge blocks get activated and the battery starts to discharge for up to when the battery reaches 40%, but the battery starts to charge again and again it reaches 80% and the next cycle of discharge begins, hence keeping the battery state of charge in between 40 and 80%. We can do this for any value of the state of charge that is required. We just have to change the state of flow diagram according to the values that are required with respect to the state of charge of the system. Another method to prevent battery fault is constant current and voltage charging. Here, the charging takes place at a constant current and constant voltage. A proportional integral controller is utilized for the purpose. Reference values of current and voltages are taken and given into the PI controller, which is given as a feedback to the PWM generation unit, which in turn controls the switches and thereby the rate of current and voltage that has been passed into the battery. So the rate of change of current and voltage equals 0. In A, B, and C versions of figure 10, we can see that the value of state of charge of the system keeps on increasing on simulation, which is shown in figure 10A during the time. And in figure B and figure C of figure 10, we can see that the voltage and current remains constant, thereby help in reducing the heat produced inside the batteries, which in turn prevents thermal runaway in batteries. To conclude, we can compare the levelized cost of energy for a conventional grid setup and that of a standalone system like our proposed model. For a conventional grid setup, the levelized cost of energy would cost you around $0.10, and for the proposed standalone system, which would be a much cheaper value than the conventional grid. But when we factor in the cost of installation, operation, and maintenance of a full-scale grid for a very small community, it would seem illogical to go for a conventional grid setup. Instead, standalone hybrid system would be a much better choice. Some improvements that can be made to the current renewable energy systems so that the quality and the reliability of these systems can be uh, improved to take away the intermittent nature of the energy that is being provided to these systems. And we can introduce better practices for controlling the battery charging and discharging process by using faster switches and better algorithms, which will further extend the life of batteries. I hope that you have understood some of the basic ideas regarding the state of charge control of batteries and how to do a techno-economic analysis for a small community and how a hybrid system is a very capable system for operation for such isolated communities where it is very difficult to install conventional grids. I thank you for your time.